In a previous video, I've proved that the pumping lemma works, how it works, and how to apply it, and I left you with 2 questions. In this video, I'll be going over these 2 questions and giving the solutions to them. I hope you've had an attempt. If not, please do. It's only for your own benefit. But now I'll be going through the solutions. The explanations will not be as detailed as it was in the previous video, as this video is not here to explain the pumping lemma, but just to provide you with some answers. So if your understanding on pumping lemma for context-free languages is not yet solid, please do watch our previous video. So let's get started. The first language here is a language consisting of a block of A's of length n, m number of B's, followed by the same sized block of A's and B's again. The only condition here is that n and m can be any value. N can be greater than m can be greater than n. They can be of the same length, but they have to be values that are greater than or equal to 0. So they just have to be a natural number. Using the pumping lemma to prove that this language is not context-free, we have to first assume that it is. Next, let k be the constant from the pumping lemma, which represents the length of a word which is in this language. For our convenience, we can say this chosen word, call it Z, has a block of A's and B's where n and m is of the same length, but because this word has to be at least k long, we can say this word is a to the k, b to the k, a to the k, b to the k. Although this is what I will be choosing Z to be to go through this solution, Z could be any word in this language of your choice. It could have just as easily been a to the k, b to the 2k, a to the k, b to the 2k, as long as the blocks of A's are of the same length and the blocks of B's are equal in length. Additionally, the length of this word Z also has to be at least greater than or equal to k. This word we know is in this language because the blocks of A's are of the same length and the blocks of B's are also of the same length. And this word is indeed at least k long. In fact, it is 4 times the length of k. Now, by the pumping lemma, we should be able to decompose this word Z into 5 subparts, u, v, w, x, and y, such that the middle section is less than or equal to k in length, and the sections we will be pumping up, v and x, have to be at least the length of 1 combined, so not both of v and x can be the empty word. And if this is true, then pumping v and x by any I that is an integer greater than or equal to 0, this pumped word that we construct should also be a word that is in this language L. We have to consider all possible decompositions of the word a to the k, b to the k, a to the k, b to the k. In this case, there are 2 ways we could decompose this word. Either v would contain some a's along with some b's, or v would contain only a's or only b's. The same thing applies for x. Remember, v and x are the 2 sections that we will be pumping. If v contained both a's and b's, pumping this word to give uv squared wx squared y would result in a word that is not in the language. This is because if v was composed of both a's and b's, pumping it twice would give you more than 3 switches between a's and b's. The first switch is from A to B, the second switch is from B to A, the third switch is from A to B at the very end. What this means is, instead of having 4 sections with 2 blocks of A's and 2 blocks of B's, there will now be 3 blocks of A's and 3 blocks of B's. This breaks the form of the word, so pumping this decomposition by any number of times would always give you more than 3 switches between A's and B's. To preserve this form of 2 blocks of A's and 2 blocks of B's sandwiched between each other, V would have to be composed of only A's or only B's, and the same applies for the X's. X would have to be composed of only A or only B. But now, u v squared w x squared y will be equal to a to the k plus I, b to the k plus j, a to the k plus l, b to the k plus m, where at most 2 of I, j, l, or m cannot be equal to 0. And if there are 2, then they are consecutive. But if not 2, then at least 1 has to not be equal to 0. What this means is, it will break the proportion of the 4 blocks of letters being of the same length. At least one of the blocks of letters will be out of proportion from the others, or at most 2 will not be equal to k anymore. Therefore, a to the k plus I, b to the k plus j, a to the k plus l, b to the k plus m is not a word in the language. This is a contradiction, because if this word was context-free, pumping this word would give you another word that is also in this language. So our initial assumption must have been wrong. This language L is in fact not context-free. So using the pumping lemma, we've proved by contradiction that this language is not context-free. So now we can move on to answering the next question. The language here is a to the n, b to the 2n, c to the 4n, where n is greater than 0. So each block of letters is twice the length of the block of letters prior to it. To prove that this language is not context-free, we have to again initially assume that it is. Let k be the constant from the pumping lemma. Next, we have to choose a word z which has the length of at least k, if not longer. We can let this word z be a to the k, b to the 2k, c to the 4k, which we know is a word in this language L, and it is longer than k. In fact, its length is 7 times that of k. By the pumping lemma, we should be able to decompose this word z into u, v, w, x, and y, such that the length of v, w, and x, there's a typo on the screen, it shouldn't be u, v, w. The length of v, w, and x should be less than or equal to k. The second condition of the decomposing of z is that the length of v and x combined should be at least 1 alphabet long. If these two conditions are met, then pumping v and x by any I that is greater than or equal to 1 will give a pumped word u, v to the I, w, x to the I, y that should also be in the language L. Now, we're going to consider all possible decompositions of v, w, and x. If v, w, and x consists of only a's, then pumping the word to give u, v squared, w, x squared, y will produce a word that is not a part of the language, because the proportions of a's are no longer half of the length of the block of b's or a quarter of the length of the block of c's. If v, w, and x consisted of only b's, then pumping the word would again not be an element of L, because this time b is out of proportion from the block of a's and c's. If instead v, w, and x consisted of only c's, for the same reason, pumping this word would result in a word that is not in the language L, because this time the block of c's is out of proportion from the block of a's and b's. If v, w, and x contained some a's and some b's, then pumping this word would also not be an element of L, because this time the separation of a's and b's and c's is not preserved. We may have a block of a's, a block of b's, followed by another block of a's and another block of b's before ending the word with a block of c's. If v, w, and x contain some b's and some c's, then similarly, pumping this word will also not be in the language L, because this time we may have a block of a's followed by a block of b's, a block of c's, another block of b's, another block of c's before ending with a block of c's. Finally, we can conclude that in all the above situations, regardless of how we decompose the word z into u, v, w, and x, if v and x consist of some a's and some b's, or some b's and some c's, then the segregation of the 3 blocks of letters is not preserved. If v and x is instead decomposed in such a way that they consist of only a's, b's, or c's, pumping such a word will result in a word of the form a to the k plus e, b to the 2k plus f, c to the 4k plus g, where e, f, and g are natural numbers, and at least one of them has to be a value that is not 0, and words of this form will not be part of this language, because at least one of these blocks of letters will now not be in proportion to the other 2 blocks. This is a contradiction, because if this language was context-free, then pumping a word from this language by any integer value would result in a pumped word that should also be in this language. But because it isn't, we can conclude that our initial assumption was wrong, and that this language is in fact not context-free. And with that, we've completed these 2 questions and shown that these 2 languages are not context-free. Thank you for watching. Please like, share, and subscribe if you found this video helpful. Please comment with any suggestions, requests, corrections, constructive criticism, anything. We'll try and respond as soon as possible.